Hello, everybody. Welcome to the webinar for Chemistry 2 in Converge version 2.4. One thing I need to mention at the beginning is because this is a one-way broadcasting, so I'm not able to take the questions interactively. If you have any questions or comments, you can text in the text box here, and I will reply to you after the webinar. Okay, let's get started. So the motivation for this webinar is, I think for a lot of people running CFD cases, especially for engine case, when they try to set up a case, there's questions in which mechanism should I pick? And the second question is, even you pick a mechanism, run the cases, what if the simulation results is not as good as measurement, and how do you tune the case, or what can you do with the mechanism to help you improve the simulation results? So these are two questions I'm trying to help you to answer during this webinar, because I think these chemistry tools sometimes can be really useful for the simulations. It can help you validate or test, even optimize the mechanism for your simulations. There are about 5 chemistry tools I'm going to cover today, as you can see from screen. First one is 0D adiabatic homogeneous reactor. Second one is 1D laminar Flamespeed. Third one is mechanism reduction. And it's mechanism optimization. The last one is mechanism merge. The first two are more basic type of the tools. The reduction, optimization, and merge are basically built based on 0D and 1D simulations. It can be involve more high-level skills, but I try to cover it here and show you some examples, help you to understand how it's going to work and how it's going to help you. So first is 0D simulations. So for 0D adiabatic homogeneous reactors, it's really simple reactors, but it can be really useful. For example, once you have a mechanism, you want to check the ignition delays of the mechanism because you may run in a diesel case. Also, if you use some combustion models does not have the mechanism built in, or it does not require mechanism, and you still want to predict ignition delays, and tabulating ignition delays are typically the way to go. And this is also you can use for 0D reactor for checking adiabatic flame temperatures. If you get a mechanism, you want to know the maximum temperature for you in order to say you may increase with NOx. The last one is the check equilibrium status. You know the unburned products and what's going to be burned products or what's going to be burned temperature. So all these you can use 0D adiabatic homogeneous reactors without running a real 3D simulation or spend a lot of time to do the calculation. There are 4 types of the 0D reactors in Converge. So first one is constant volume and constant pressure. Third one is constant temperature, and the last one is chemical equilibrium. For the constant volume, as indicated from the name, so basically system volume remains constant during the whole combustion process. And the temperature pressure are going to increase. And for this type of reactor, the temperature will be highest and the equilibrium compared with constant pressure and the constant temperature, because there's no work output from this kind of reactor. On the right is trying to show an example. Let's say we have 2 mechanisms. one is from Wang 2015, and another one from Mel from 2011. And for some conditions, how do we know which mechanism performs better for me or for the case you're trying to solve? So basically, you can run a 0D constant volume case and plot the ignition delay along the temperature. As shown here, you can see both mechanism does good job on high temperature area, but and the NTC area, the Mel mechanism is better than Wang's mechanism. So this is just an example to demonstrate without running a 3D case, how do you roughly know which mechanism works better for you? Similar to constant volume, the constant pressure, constant temperature. For a constant pressure reactor, the pressure keeps constant during the ignition process. And for the constant temperature, the temperature keeps constant. So the pressure and density varies during the combustion. On the right is showing a shock tube specialization. Basically, this is constant pressure application. The dots are from the measurements, and the line is from the simulation. You can see even for 0D simulation, we can have pretty good results to measure the measurement. The last reactor for 0D reactor, or I kind of call it a 0D reactor, is chemical equilibrium. Basically, the definition of equilibrium is the species concentration do not change with time. And we do have two options for chemical equilibrium. You can solve equilibrium for constant pressure and temperature, or you can solve the equilibrium for constant pressure and constant enthalpy. On the right, there's a plot. So basically, the y-axis is the mass fraction of the CO, and the x-axis is the progress variable. For the people who don't familiar with the progress variable, basically, it is a progress of the combustion. And 0 value, everything is unburned, and 1, everything is burned. So this plot is trying to demonstrate the differences between a transient 0D solver and a chemical equilibrium. For transient 0D solver, similar to constant pressure, temperature, constant volume, I just talked a couple slides before. Those are solving transiently. As shown on this plot, you can see you actually can get any progressive variable. You can get the mass fraction of CO and any progressive variable from 0 to 1. But if you solve chemical equilibrium, you only solve for 2 points, basically. C0 is unburned, is your initial condition. And once you solve for chemical equilibrium, you only get the value and C equals to 1. It's going to jump from 0 to 1 directly. The next topic, a tool to cover here is 1D laminar Flamespeed. So in 2.4, we have several options for calculating 1D laminar Flamespeed. I'm going to cover the details just in a minute. But the first one is why we need 1D premixed flame. The first thing is for gasoline applications, definitely if you want to know the flame propagation or the flame speed or how fast your flame can propagate if you use this mechanism, you have to validate this mechanism for the conditions you are interested. And the second scenario is if you're running T equation, ECFM, or let's say, thickened flame model, okay, you may not have the detailed chemistry, and how do you get the laminar flame speed? One way is to generate the table based on the 1D laminar flame speed. Also, for another kind of combustion models is, let's say, FGM is a flamelet generated manifold. Basically, if you are solving a premix type of flame, and you have to generate a chemistry manifold, and you also can use this 1D laminar flame speed tool to generate the chemistry manifold. Basically, it has all the species information and the different progress variable conditions. What exactly the laminar flames, laminar premix flame we're solving here? So first, it is a 1D freely propagating laminar premix flame. So basically, the flame, if you look at the flame, you can think it is a planar premix flame sheet. And so in this way, we can reduce a 3D dimensional problem to a 1D. Also, we assume because the flame is planar and the moving velocity is a normal direction to the flame sheet. In the domain, we also assume there is no pressure gradient. Also, there is no temperature gradient. So everything is premixed. The bottom plot is just showing an example of the results. Basically, if you have a line plot from the one side to another side of the domain, for temperature, you can see temperature stay as an initial condition until it reaches the flame. Then the temperature ramps up to kind of equilibrium or steady temperature, and all the mixture, all the species convert from unburned mixture to the burned mixture. There are 3 ways to solve this laminar flame speed in Converge. So first is a steady state. This is more commonly used for everybody. And the second one is PISO Solver. This is what we have developed inside of Converge. And then the third one is kind of hybrid. The idea is trying to combine both steady solver and the PISO solver together to have better performance. And for species diffusion models, there are also 2 options to choose. If you have transport data and you want to solve mixture average diffusivities, you can use this. Or if you just want to use the gas style data, which you are assuming it's constant diffusivities for all the species, you can also just plug in gas data to solve laminar flame speed. First method is Newton's method. This is the steady state. Basically, we solve the 1D steady state equation, and this is the most common method to use simply because the speed. You can reach really fast converge results if you have a good initial condition provided. Also, you can also run a sensitivity analysis with this kind of method and without no extra cost. However, based on our experience, sometimes because the mechanisms have some issues or the initial conditions you don't know, and Newton solver can never reach a steady state. So there's some robustness issue. Also, because this is during solving this, we do construct, excuse me, a matrix which is size of species times number of points. If you have really big mechanism, and the memory could be a problem. So this is just a downside you need to keep in mind. This Newton method may not ideal. There are some issues when you solve the 1D flame. So for initial conditions, what we did inside of solver is we use constant enthalpy and pressure equilibrium conditions to initialize the temperature and the species and mass fractions. We assume or the default domain size is 3.5 centimeters, and the thickness of the flame or the temperature ramp up is about 10% of domain, which is 3.5 millimeters. During solve the steady state, we can extend or shorten the domain. Also, we can change the thickness or the ramp up factor dynamically in order to get a convergency. So the second one is the PISO. I have talked about because the robustness issue or the memory issue for the Newton solver, then how do we solve this problem? So we come up with the PISO solver. The PISO solver is actually just 100% based on the converge transient solver, and it also uses adaptive mesh refinement. You basically solve a transient issue instead of a steady issue for PISO solver. The benefit for this is it's really robust because it's solving transiently. Also, it does not require user to provide a good initial solution. You can basically initialize the domain as inflow condition, and because we're solving transiently, so the flame gonna propagate to a certain location and stabilize at that location. Then we see, okay, this is the final results we can get. Also, this solver is 100% parallelized because it's built up based on the converged PISO solver. This also means it does not have a high memory usage for a Newton solver. If you have really large mechanism and you have larger points, we can parallelize on several CPUs. So this is ideal for large mechanism applications. But there are also downside, of course, because it's solving transiently. There is a speed and accuracy trade-off for PISO solver. If you use very fine mesh and really tight tolerance, you do get a really accurate flame speed. However, it does take time and CPU hours to solve that final results. Then this comes to the third method we proposed here. It's hybrid. Basically, it combines the PISO solver and Newton solver together. The idea is really simple. How about just use PISO solver to provide an initial condition for Newton solver? In this way, we do not necessarily have the accuracy and the CPU hour trade-off. Also, it may solve the robustness issue from the Newton solver. To set up this hybrid solver is easy. So basically, just inside of Convergent Studio, you just need to run the Newton setup and the PISO setup together. So it will automatically run the PISO first, then use the PISO results as the initial condition for the Newton solver. However, there's one thing we need to keep in mind for this kind of hybrid solver is it still has a limitation on the memories. Because the last step, we still solve the Newton solver, and we still require the memory size about the square of the species times number of points you have. Showing example for 1D flame speed application is 1D flame speed table generation. For some models, you have to either use correlation or something to get a flame speed. And providing a flame speed table is considered a more accurate way because you can run detailed chemistry for all the conditions you are interested. So now we have the capability to generate a flame speed table. basically, you just need to use 1D template.in. So in this template file, you are able to specify the pressure points, temperature points, equivalence ratio, or feed points, as well EGR points. Okay, and we do support more than one field. Actually, you can do dual field case if you want to generate the table. And all the flame speed data will be output or saved in HDFI format once it's completed. And we have a utility to help you visualize the results after that. Because we by default we use Newton solver to solve. Sometimes you will say if you run 1,000 points, they may have like 1, 2, or 10 points are not converged or not have results. So it allows you to restart these separate points to finish your table. All the Flamespeed table, if you're running converter for engine simulation, you can couple with the G equation, ECFM, and the FGM. On the right is showing an example for running with the G equation plus flame speed table. You can see with this flame speed table, it can recover the baseline results really well. The third topic here is the mechanism reduction. As you know, the development of mechanisms, people tending to have larger and larger mechanism right now, and for some gasoline, diesel, or biodiesel case, there might be hundreds and thousands of species and reaction in the mechanism. But this is really expensive for CFD simulations. If you run 0D, 1D may okay, but if you run a 3D simulation, RANS, LES, it's just simply too expensive. So what can we do to take advantage of this detailed mechanism, but still make it feasible for 3D simulations? Basically, you can reduce the mechanism. The idea is because the detailed mechanism typically built for a large range of conditions, different pressure, temperature, feed conditions, and for you, specific application, you may just interested in subset of the conditions. So we can use some reduction tool to reduce the species and mechanism are not really important for the applications you are interested. In Converge, there are 3 steps to help you to reduce the mechanism. Each step going to help you remove some kind of species and reactions. The first step is DRGEP. It's called Directed Relation Graph with Error Propagation. And the second step is to run sensitive analysis on the 0D ignition. And the last step is species lumping. How does excuse me, how does DRGEP work? The DRGEP basically considers the propagation of error due to species removal down reaction pathways. For example, we have a species A and it's important. We want to keep it. So we list as a target species. Then we can build a species tree based on the reaction path. As I say here, there are about 10 species from A to J. And each species has a weight factor to its neighbors. Basically, the weight factor is a function of reaction rate and coefficients. Basically, it's saying how important your neighbor is for generating or consuming the species A. For example, let's say how important the D is to species A. Then we define a variable called path-dependent coefficient. Basically, it's looking for all the possible path from D to A, or you can say A to D, and weight them in this path-dependent coefficient. If we say if this coefficient is below 0.1, we can define this point, the species or path are not important at all. And for this specific example, we can remove 4 species, basically G, H, I, J, and then we end up with 6 species after running the DRGEP. So after DRGEP, we list all the species together. Okay, we have really important species, and by using DRGEP, we have unimportant species. But you're gonna see there's still a big chunk of species in the middle between important and unimportant species. We call these our limbo species. Limbo species can be important or can be not important at all based on the conditions you're trying to pick. So what we are doing here to run the sensitive analysis to figure out which species is actually important for the conditions we are interested. And the way to do this is we remove each species and calculate ignition delay and get the error from removing this species. And we sort all the species based on the errors. So once we have the species list, then we start removing species from the bottom of the list, which has the minimum errors. We can remove first one, check the error, then remove second one, third one, fourth one, until the error on ignition delay is exceed the tolerance we specified. It can be 10%, 20%, or 50%. Really depend on what kind of mechanism size you are looking for. So by the end, then we have the final mechanism. So the last step is isomer lumping. The idea is even we reduce the unimportant species, and we also remove some limbo species. But if you look at all species, there are still a lot of species have similar properties. And so the idea of isomer lumping is instead of solving for 5 species, if there are 5 species have similar properties, we can just solve 1 species instead of 5. You not only saving the time on chemistry calculation, also you save time on transport. You only transport 1 species instead of transport 5 species. After the lumping, you can, because this is really simple strategy, and if you want to back up to the original species in the isomer groups, you can just simply times the factor, which is determined by statistical analysis. This is just an example of what the final mechanism looks like after lumping. You can see instead of a species name with CH, so we name as start is always start with ISO, which is short for isomer, and it depends on the groups you have. You can have a ISO 1, ISO 2. In this example, we have 7 isomer groups. And in the reaction, the species group in the isomer group going to be replaced with the group name. You can see here it's ISO 01. And there's keywords after reaction. It's called lump. And there's the alpha factor. Basically, this factor going to be used for reaction calculation, which showing on the left. Basically, you need when you calculate the rate of the lump reactions, then you need divided by this factor. An example of the reduction, for example, this is the Lawrence-Livermore gasoline mechanism. A lot of people use this. it has over 1,300 species and it's 6,000 reactions. If we say we have some important species listed in the table here, basically we have the fuel oxidizer, and we have all the C1, CO species listed, total 36 species. We say these are important species, and we reduce this temperature from 700 K to 1300 K, pressure from 5 bar to 55 bar, phi from 0.5 to 2. We can get, there are two example reduced mechanisms here. So first one is a 573 species, and second one is a 472. All the setups are same to reduce these two mechanisms. The difference is only on the error tolerance we specified during reduction. With tighter tolerance, we get 573 species. With loose tolerance, we get 472 species. So then we run the ignition delay and laminar Flamespeed to check how the performance of these two species, two skeletal mechanisms. You can see from the ignition delay time plot, on the high temperature and the low temperature area, the 500 species, 400 species all do a good job on the ignition delay prediction compared with original mechanism. However, the differences is showing near 1,000 K or NTC area. You can see 500 species does significantly better than 472 species mechanism. This is just simply because 500 species skeletal mechanism, you use tighter tolerance. So this is one way to tell you, okay, if your engine running conditions or the condition you are interested is not near the NTC area, then it's 100% okay to use 400 species. But you do get a lot of conditions in the NTC area, then you have to basically stay as a 573 species mechanism. In terms of the flame speed, they all does a pretty good job. There's no significant difference between the reduced mechanism and the Lawrence-Livermore original mechanism. Second example for reduction is isomer lumping. Some people think maybe isomer lumping is not necessary. This is just a slide demonstrate. Sometimes it can be quite helpful to reduce the mechanism. Let's say for biodiesel mechanism from Lawrence-Livermore, there are about 1,500 species. However, there are actually 50% species are isomers. I have some statistic plot on the right. Basically, it's showing number of isomer groups versus the size of isomer groups. You can see there are a lot of isomer groups, but you can see also there is some isomer groups has a lot of isomer species. And for example, once we reduce this maximum after DRGEP and sensitive analysis, we reduce from 1,500 species to 472 species. Then we run isomer lumping on this reduced mechanism. We can reduce the mechanism to 3 to 6 species. It's almost 20% reduction in terms of the number of species. The next topic I'm trying to cover here is the optimization. Why we need optimization on the mechanisms? I think the first more intuitive answer is we reduce the mechanism, and it's not free, right? You do introduce errors for the reduction. If you reduce the mechanism, by specify lot of points, lot of conditions, you do have a really accurate mechanism, but the size can be big. So sometimes people use less points, or if you use loose tolerance, you get a small size mechanism which is considered to be affordable for the 3D simulation, but it potentially can have a lot of errors. So in this way, I think this is the good example to use mechanism optimization. The reason is it can improve the accuracy of your reducer mechanism without actually increasing maximum size. Or there is no actual computational cost once optimization is done. It's different from reduction because you say your maximum is not accurate. If you want to reduce again, you may end up with adding more species to reach that accuracy. But running the optimization, there will be no species or reaction added. Also, the optimization has a lot of options. You can optimize your mechanism based on 0D ignition delay, or say you are more interested with laminar flame speed. Sometimes people running simplified 3D results, 3D simulations, and you don't know what to optimize on, then you can simply just use your 3D results or what kind of results you're expecting from 3D simulation as the target to optimize your mechanism. So in Converge, we achieved optimization by using this 0D, 1D utilities and the Congo. Congo basically is a generic algorithm solver. This is a big picture of the optimization. So first, let's say you have an original mechanism, okay? And the first step of optimization is to run sensitivity analysis to get what factors are important for your simulation. And these factors are going to be used or going to be modified for the better accuracy of performance. So sensitivity analysis can be done on ignition delay or laminar flame speed. And by running this, so you select a reaction constant from the most sensitive reactions, and these are the inputs to the second step. Second step is optimization. And we use Congo. So the results from sensitivity analysis are going to be combined with the targets you specified. The targets can be the ignition delay or laminar flame speed, or can be any measurements you want to meet by running your mechanism. So after running with Congo, by the end, you will have an optimized mechanism. So what does sensitivity analysis do, and what kind of method we use? So for 0D sensitivity analysis, we use A-sense. Basically, you can run sensitivity on species or the temperature. The advantage of A-sense over the forward sensitivity is it's much faster, and there is not a lot of output, so you don't need analysis all the information. It will give you small output files. On the right is showing an example for PRF mechanism. So we run sensitivity on the temperature, and the condition is constant volume, 900 K, 20 bar, and enter stoichiometric. So we list five reactions which are most sensitive to the temperatures. The top 5 are most sensitive because they have negative sensitivity coefficients. So they actually more sensitive to reduce the temperature. If the temperature increase, the red 5 reactions are more sensitive. For 1D simulation sensitivity analysis, basically we are doing sensitivity on A factors. The A factor is, when you recall the form of Arrhenius form, that's the first factor in the equation. It's called reaction rate coefficient. So basically, sensitivity is estimated based on the first point of the 1D domain, is unburned point. On the right is showing a result from sensitivity by running GRI 3.0. You can see from this point, we can, let's say, if we pick top 5 reactions, gonna be the reaction I'm trying to optimize, then you can pick from there. This table is showing the combination of the possibilities for the targets and the sensitivity analysis. So if you want to run Congo, right, there are 2 inputs. One is sensitivity. You need to tell Congo which factors to optimize. Or second one is the targets, what kind of targets you are trying to meet. So this table is trying to show if you are running 0D sensitive analysis, and for the targets, you have to specify on 0D. Similar, if you only do 1D sensitivity analysis, then target has to be on 1D. However, if your target's on both 0D and 1D, right, then you actually have the possibilities to do any combination of the sensitivity analysis. This slide is going to tell you what exactly optimization has been done. So basically, it's a Congo. It's an automatic process to optimize the targets, optimize the sensitivity results based on, and trying to meet with the targets. It's using generic algorithms and launch converge. So on the right is showing a chart flow. Once you have the input file set up for Congo, and the Congo will automatically launch the converge for all the conditions. And once the converge is done, it's going to collect all the results and evaluate the results compared with target. Basically, it's showing as a merit function or merit value. So if the result is not good or it's not as good as expected, so it's gonna do this over again. So it's gonna get the input and change the sensitivity, change the factors from sensitivity and run converge again, and then evaluate the final results compared with targets until there is the best or there's kind of acceptable results. Then we can stop the Congo. Using generic algorithm for this kind of optimization is very high efficiency. So it's also it's very effective. For running 0D 1D, you really get really short return time for a lot of generations. To set up the optimization, there are 2 steps which will be different from your previous experience if you had the experience with the converter setup in the studio. Basically, it requires you first to set up 0D 1D in the studio and run the convert. Now you can close the studio, get input files, run the converter with sensitive analysis, and the converter will output all the sensitivity A factors for you. The second step is you have to open the GUI or the Converge Studio again to import the output files from previous run and set up the Congo. Then you can close save all the output files for input files for Congo and run the Congo for the optimization. First example for the mechanism optimization. let's say we have desired flame speed as shown as the blue here. And we have Jia PRF and TRF 2 mechanisms. Obviously, they are not even close to what desired flame speeds are. So this way, we run the sensitivity and optimization on PRF and TRF on these conditions. And after optimization, and we rerun the flame speed, you can see they are getting reasonable close to the desired value. Second example is a 3D spray bomb case. Basically, it's a spray A. We have the original mechanism for this spray case, which is shown as a red line here. And the black dots are experiment. And we reduce this mechanism to like about 100 species. And we run the 3D spray case again. Then you can see the ignition delay as shown as blue here. It's getting off because the error introduced from reduction. Then we launch the optimization for the optimization is only on the 0D ignition delay for this specific case. We run the optimization, then we get the green curve here. Basically, you can see it's getting close to what original mechanism predicts. For the lift of length on the right, it's basically showing the same trend. Right? For the original mechanism, it's showing as red. The blue one is right after reduction. Then we run the optimization, and the green line shows the lift off length after optimization. You can see it improves the lift off length. The last topic I'm trying to cover here is mechanism merge. Mechanism merge, it can be easy, it can be tedious. It's really depends on what the scenarios are. So there are typical 3 scenarios I can think about where you should use mechanism merge tools here. So first is I have 2 mechanisms, right? And I'm trying to develop a multi-component surrogate mechanism. And one way for surrogate mechanism is I just simply merge 2 existing mechanisms together to achieve this. And if the mechanism is really big, so then you have no way, just do it by hand, manually. And so here you can use the tool. Second way is because the detailed suit model, we have pH or detailed NOx models. And for these models, we're trying to apply to different mechanisms. And how do we attach the soot or NOx mechanism to other mechanisms? The third scenario is I have a mechanism and I come up some thing here, and I try to just add extra reactions into my mechanism. And how do I add this mechanism without breaking original reaction path? So this is the tool can help you. During the merge, so there are 2 ways in Converge to help you. So the first way is using Convergent Studio, which I personally like this better than the second way because it's more intuitive. And you can see all the conflicts, just visualize all the conflicts. Second way is using utility, Convergent utility. Basically, you do everything through the command line. And this is more efficient way if you're really familiar with what you are doing. And this is the best way because it doesn't involve a lot of visualization. You just can do everything through the command. But no matter which method you are using, there are typically 4 steps involved. So first one is getting 2 mechanisms and the thermal data associated with each mechanism. And later, you have to resolve the conflicts, right? So first, you need to resolve the conflict on the species. And the second, you need to resolve the conflict on the reactions. The conflicts can be different, really depend on how you merge 2 mechanisms. First, if you just simply want to put 2 mechanisms together, you can do that. Or I have a mechanism, and I don't want to break the pathway in this mechanism, and I'm trying to add a second mechanism on top of the first mechanism. So these are 2 different ways to merge. So by the end, after merge, so you can output the mechanism through Studio, or if you use utility, it will automatically generate the final mechanism for you. As we're resolving the species conflicts, there are 3 scenarios. So first is same element conflict. What does this mean? It means 2 species names can be different, right? But if you look at thermal data, they actually have the same conflicts, same element conflicts. They have exactly carbon number, hydrogen number, oxygen number, or nitrogen number. So it literally is the same species. The second conflict is same name conflicts. Okay, if you look at mechanism 1 has 1 name, second looking at the second mechanism, Mech 2 has the same name. However, if you check the thermal data, they have different elements. They may have different. One may have the hydrogen element in the Mech 2. There may not have the hydrogen element there. The third scenario is this is simplest. So name and elements are completely different in 2 mechanisms. So if you use a GUI, this is what I like. Why the reason I like to use GUI. So if once you import the 2 mechanisms together, so all the species will be grouped, and you can actually tab through each group to look at how many species has same elements conflict, how many species have same name conflict, and how many species are unique for each mechanism. Then come to how we merge mechanism. So first is we just simply want to merge 2 mechanisms together. There's no baseline mechanism. I just want to take all the species from 2 mechanisms, put them together, and also take all the reactions, put them together. And you can see I have an example here. I have Mech 1, Mech 2, and they have the identical species name, identical reactions showing in red, right? Also, I have the bold black in species in Mech 2. The species name is in bold font, and the reaction in bold font, and they are showing unique species and reactions in Mech 2. Also, showing as green in the reaction is so we have similar species in Mech 1, similar species, same species in Mech 1, same species in Mech 2, and but the reaction which has these same species are different in Mech 1, Mech 2, and I'm trying to merge together. In this scenario, we actually just take everything together. You can see the green comes into the final mechanism. So you can see by the end, we get the final mechanism in the middle. It has all the species from Mech 1, Mech 2, has all the duplicate reactions from Mech 1, Mech 2, also has all the unique reactions from Mech 2, and to form the final mechanism. The second way is what if I only want to merge Mach 2 into Mach 1? Because let's say if I have a mechanism, I don't want to break the ignition delay, but I do want to improve some flame speed. So I may want to just merge second mechanism into first one without breaking the reaction path. So basically, if you want to do this, as in the example here, let's say the final, we have the Mach 1 as base, Mach 2 is a mechanism we're trying to merge. In the middle is the final mechanism we have. You can see all the Mach 1 reactions are kept in the final. Only the reaction and the species unique from Mach 2 got merged into the final species. Because there's a CH3 plus CH3 reaction in the Mach 2 does not come into the final mechanism. The reason is simply because the CH3 is existing in the Mach 1. So basically this means we are kept CH3 mechanism. We're just trying to reserve all the reactions in Mach 1 for CH3 without breaking during the merge. So we get rid of the CH3 mechanism in Mach 2. This is what you're going to see when you're trying to resolve the reaction conflict or species conflicts in Studio. If you merge both, if you merge a second mechanism into the first mechanism, you actually, most time you do not see any conflicts because the GUI is smart enough to help you identify what to keep and what to remove. However, if you want to just simply put two mechanisms together, then you have to resolve the conflicts manually. Basically, in the GUI, it's going to show all the conflict reactions and the species. You have to pick which reaction you want to keep by clicking 1, 2, 1, 2, 1, 2, one by one here. Trying to show example here. I have two mechanisms. One is isooctane, one is n-heptane. And I want to merge n-heptane mechanism into isooctane. So here's the results for the ignition delay and the flame speed after merge. Basically, you can see the merge mechanism showing as green. The isooctane mechanism is showing as red, and n-heptane mechanism is showing as a blue. So after merging the n-heptane mechanism into isooctane, I actually, for the ignition delay part, I actually reserve all the ignition delay from the gasoline or isooctane mechanism. And this is what we're going to expect by using the second merge method. Just keep one baseline and merge the second one into the first one. However, the flame speed obviously messed up. You can see after the new mechanism, it does not predict any flame speed close either one. So in this scenario, I mean, one solution here is run the mechanism optimization on the laminar flame speed. Let's say if you want to keep the, you want to predict, you want to keep the flame speed as more like gasoline, then you can run the optimization and set gasoline mechanism flame speed as a target. So by the end, it will bring the flame speed down to the right line. This is the last slide I'm going to cover here. Basically, you can see all the options by typing dash question mark to view all the options for utility here. And also we support NASA 9 format in Converge 2.4. So you're going to have more freedoms to have different format of reaction and thermal data. the references, and that's all. Thank you for everyone.